through a problem set where we do a bunch of F equals ma equations and tie it to 1D motion, and we look at net force in general. One of the keys here is when we get into the combination problems, you're going to have enough information either to solve for acceleration using the 1D motion equations, or you're going to have enough information pretty much if you're given F and M, you can always solve for acceleration, so you might need to solve for that way. So we'll see those in a little bit. Let's go ahead and start off with some basic ones. So here we have a 15 kilogram mass, and we have a 500 Newton force, and we're asked for the acceleration. So A equals question mark, M equals 15 kilograms, F equals 500 Newtons, and then we have the F equals ma. We can rearrange that equation. So when we're solving for A, we're going to divide out the M, and when we divide out the M, we're going to get A equals F over M. Plug in the numbers, and for this first problem, you get 33.33 meters per second. In this case, it's right because we knew it was right before. Force creates an acceleration in the direction of that force. So that 500 Newton force was to the right, so that's why it's right. If you ever see magnitude, it's just leave off the right part. But here it asks you for the actual force. Okay, here's the next problem. Same sort of deal. We're asked for acceleration. We're given a mass of 25 kilograms. We have a force of 50 newtons to the right. So we're going to do the same equation, same rearranging. And when you plug in the 50 over 25, you're going to get 2.0 meters per second to the right. Okay, and then here we have, now we're talking about net force. Once again, it's F net equals ma is the equation. F net equals ma. Often you'll see me just put F equals ma, but you have to have the overall. And when you have two forces, you're going to figure out the overall. So 55 newtons left and 25 newtons right. We can call the left negative and right positive, add those numbers together, and we get 30, a negative 30 or 30 newtons left. So our overall acceleration here is going to be to the left when we solve for everything. We're solving for acceleration. We have a mass of 3 kilograms. We have a force of overall, once again, we solved for this earlier, 30 newtons, and this was to the left still, so it's going to be in our final answer. We have F equals ma. We can rearrange F equals ma just like before, and we get 30 over 3, and that equals 10.0 meters per second squared to the left. So the next problem, we have two people pushing on the same side, so they're both going to the right. Since they're both going to go to the right, you add them up together, and you get 75 newtons to the right. Now we're going to use that to find our acceleration with our mass of 5 kilograms, and we have a force of the 75. So we go to F equals ma, we rearrange the equation again, and we get 75 over 5, which ends up being 15.0 meters per second squared to the right. This problem right here, we have a 25 kilogram box, mass of 25 kilograms, and there's two forces, 100 newtons north and then a 50 newton to the right, and we have to put those together. In order to put those together, we're going to have to turn it into a right triangle. So and we're going to go ahead and we're going to make it draw it head to tail. We're going to draw an origin dot, and then we're going to go ahead and draw our first vector. I'm just going with 50 newtons. It really doesn't matter, but if you want to check your answers with mine, 50 newtons east first. And then we're going to follow that up by 100 newtons north. We're going to draw in our resultant, our overall magnitude of the resultant. We throw in our angle so we can solve for the second part. And then we want to find C. And so we're going to do the Pythagorean theorem, C equals A squared plus B squared. Throw in our numbers, 100 squared plus 50 squared, take the square root of that. And you're going to get 111.8 newtons. This is going to be your overall force that's the result of this 100 newtons and this 50 newtons. Now we want to find the acceleration. So this right here would be considered the net force. So we want to take the acceleration, find the acceleration from that. We go ahead and take A equals F over M. We rearrange this top equation, divide out the M from both sides, divide out the M. We get A equals F over M. And then we can go and plug in our values. So we can plug in the 111.8 over 25. And we're going to get an acceleration of 4.472 meters per second squared. And then to figure out this direction, we're going to have to determine what our opposite, our adjacent side. We're going to have to do inverse tangent. We're going to want to make sure that our calculators are in degrees, not radians. We plug in and we figure out, okay, this angle opens up to the opposite, the other side's adjacent, so this 100 is going to be my opposite. So inverse tangent of 100 over 50, and you're going to get 63.43 degrees. And then the direction is going to be north of east. Once again, the last thing you see in the direction is actually the first thing that comes out of the origin dot. So north of east would be the answer. And if I want to do a complete answer, which just doesn't ask you for a complete answer, but the actual acceleration would be 4.472 meters per second squared, 63.43 degrees north of east. Okay, which one of these? Lorinser Speedy, 6,300 kilogram elephant, the 795 kilogram Lorinser Speedy, or the 8.6 kilogram wagon would have more inertia, and that's going to be the elephant. The more mass, the more inertia. Mass is directly related to inertia. How much force is required to accelerate a 795 kilogram Lorinser Speedy by 15 meters per second? So how much force? We have our mass, we have our acceleration, and that's just straight up F equals ma. Plug in our values, and we get 11,925 newtons. How much force is required to accelerate a 8.6 kilogram wagon by 15 meters per second? So more of the same, basic F equals ma equation. Plug in our values, and we get 129 newtons. How much force does a 6,300 kilogram elephant accelerate when you apply 500 newtons of force? So we have an A that we're solving for. We have the 6,300 kilograms, which is the mass. We have a force of 500. So we have F equals ma. Now we're going to rearrange that for A. Once again, like before, we'll divide out the m from both sides, and you get F over m. Plug that in, 500 over 6,300, and you get 0.0794 meters per second squared. What is the mass of an object if it takes a net force of 40 newtons to accelerate at a rate of 0.88 meters per second squared? So we have mass that we're solving for. We have our acceleration given. We have a force given. We're going to go ahead, and this time we're going to go ahead and solve. We want mass alone, so we're going to divide out the acceleration. So that just is going to be m equals F over A. And we plug in our values, and we're going to get a mass of 45.45 kilograms. Number 11, so now we're going into it, and you can see I put the 1D motion equations down here. I didn't put the F equals ma, but we're going to use 2. We're going to figure out where we have enough information to go. And so here it says how much force is required to accelerate that. They tell you the baseball is 0.142 kilograms. And assuming we're starting from rest, it doesn't tell you that, but if you're pitching a ball, you're going to start from nothing. And you're going to get to 44.7 meters per second, which is the same as 100 miles per hour. But we're dealing with meters and seconds. And we have distance. The pitcher is going to release this within 1.5 meters of where they started applying this force. So what's going to be useful here, we're going to find acceleration. We don't have force. What we do have is we have initial velocity, we have final velocity, we have x, we have acceleration. We can use these and the 1D motion equations, and you're going to pick the equation that has the VF, VI, A, and x, which we have right here. And we pick out the equation, and we can just start plugging in the numbers. So 44.7 squared equals 0 squared plus 2 times A times 1.5. I start putting those numbers together. So this becomes 1998.09, and this is the 2 and the 1.5 multiplied together, become 3. The 0 is nothing, adding to any numbers, whatever that number is, and so that's where I get to this. Divide 3 from both sides, and we get an acceleration of 666.03 meters per second. So now that we have our acceleration, now we can go to the F equals ma. And we can just plug in our values of 142 for the mass, 0.142 for the mass, and the 666.03, and we're going to get a force of 94.58 newtons. Okay, next question. We've got some information here. We're asked, okay, the golf ball, 0.050 kilogram golf ball, leaves the tee at a speed of 75 meters per second. The club is in contact with the ball for 0.02 seconds. What's the net force of the club on the ball? So they give us all this information. We've got our mass. We've got our initial velocity because it's not moving at the beginning. It's going to get to 75 meters per second. And the time it takes is 0.02 seconds. We're going to solve for acceleration because we want to find force at the end, so we need m and a in order to solve for it. So we look at our givens. We have VI, VF, T, and A, and that's going to lead you to VF, VI, A, and T. That equation will work. So we plug in all our values. 75 equals 0 plus A times 0.02, and then when we divide out the 0.02 from both sides. We're going to get 75 divided by 0.02, and we're going to get 3,750 meters per second. Now we can go ahead, now that we have acceleration, we can go and take that mass, we can take the acceleration we just solved for, and we'll get, when we multiply the two, F equals ma, 187.5 newtons. Okay, in this problem we have a 90 kilogram astronaut that receives a 30 Newton force from her jetpack. How much faster will she be moving after 2 seconds? So we can build up a givens list from this information. We've got a mass of 90, we've got a force of 30 newtons. We're asked for how much faster. So we're going to just do we're going to kind of do a relative problem. It doesn't tell us how fast she was going, but let's just pretend she was going 0. Because if she was going 0, we're going to solve for how much faster from a 0 point. So it might not have been 0, it might have been some other velocity, but we're just going to go ahead and say VI 0. Because when we solve for VF, we're going to know the difference, which is how much faster she's going. So that's what we're doing here. 2 seconds later, and so FMA, oh look at this, we have M and we have F this time. So we can go ahead and we can go to F equals MA to this equation. And once again, rearrange it, divide out the M from both sides, you get A equals F over M. You plug in your values, and so you get your values right here, 30 and 90. And you get an acceleration of 0.333 meters per second squared. So I left it out, but it's meters per second squared. And then in a little bit, let me finish this video first, okay? And so we have our equation that we're going to go to. So we have A, we have T, we have VI, we have VF we're solving for. There's everything we need in this equation. So we go ahead and plug in all our values. VF equals 0 plus 0.333 times 2. And we get 0.667 meters per second. So this is how much faster they're going. So it's not how fast, I don't know how fast they are actually going. I know that they're going to be going 0.667 meters per second faster at the end of this force being applied for 2 seconds. Okay, a 795 kilogram car starts from rest and travels at 41 meters in 3 seconds. How much force did the car engine provide? And you can already see the work in the answer. So let me just go ahead and show it all since I had it kind of out of order. So I'll fix this later. And so we have our information. So let's say we have F. Okay, we're missing too many things. We're missing F and A. We're not going to be able to start there. But what we can do is we can go ahead and figure out, use FVI, X, T, and A to find an equation. We look at these equations right here, and when we look at those equations right there, that's going to lead you to this equation. So you have your X, your VI in it, the T, everything we need to use that equation. So there we start plugging in our values for 45 meters for the X, the 0 for the VI, the 3 for the time, and we have the 3 for the time here. So we'll go ahead and multiply this out. This is going to cancel out, and then 3 squared, we have 9 times a half, which will give you 4.5a. So 41 over 41 equals 4.5a. We do the math, we divide out the 4.5, we get 9.11 meters per second. So once we have the 9.11 meters per second, we now have the A part of the F equals ma, and so we can go ahead and do the 795 times the 9.11, and we get 7,242 newtons as our answer here. Okay, so here we have Joe sailing a sailboat who has they have a combined weight of 450 kilograms. How far has Joe sailed when he started at 5 meters per second and a gust of wind power provided 600 newtons of force for 4 seconds? Okay, so how far has Joe sailed is going to be X. We got some other information. We got the mass of the sailboat, 450 kilograms. He started at 5 meters per second, so this is not one of the problems where he started from rest. We have a force of 600 newtons. This is going to be provided for 4 seconds. We're trying to find out how much further he is. And so we take a look. We got mass, we got force. Okay, well, look at this. We can go ahead and we can solve for A this way because we have F, M, and A, only one unknown. So we'll rearrange that, divide out the mass from both parts. A equals F over M, plug in our force, plug in our mass down here, and we get 1.33 meters per second. So now that we have the acceleration, we can look for an equation that has, we're solving for X, we need T, we need VI, and we have A that we just solved for right here. And so we have X equals VIT plus 1/2 AT squared. So this has all of our information that we have circled over here. All these things are in here, so I can go ahead and use this right here. So I plug in my values, And when you solve all this, plug this all in, you get 30.64 meters. So this is how far Joe would have sailed in this sailboat after that gust of wind hit. Here we have Tom pulling a 45 kilogram wagon with a force of 400 or 200 newtons at a 15 degree angle to the horizontal. So we need to find this component of this. So it's 200 newtons this way, but that's not going to go into acceleration. Some of that is going to help lift this wagon off the ground a little bit. Not going to actually lift off the ground, but it's going to provide some force that the ground doesn't have to push against it. This is going to be useful for that part, the Y part of this, the upward part of this. That'll be useful when we get to our friction unit. But for now, all we need to know is this one right here. We can find the horizontal component. That's the direction the motion is going to occur. So let's start by doing a little SOHCAHTOA, drawing out the triangle, 200 newtons at this angle. But what we want to find is this horizontal force. So we have our hypotenuse and adjacent. That's going to lead us to adjacent equals cosine angle times hypotenuse. We plug in our values, cosine 15 times 200. Once again, make sure you're in degrees, and we get 193.19 newtons. And now we have a force that we can use in our equation. So we pull all this other given information. It's a 45 kilogram wagon. It's going to start from rest here. We have a time of 2 seconds. We have a final velocity. It's trying to see how much will the wagon be, how much faster will the wagon be moving after 2 seconds. So we're going to solve for VF. And looking at this, we have F, we have M, so we can go ahead and start with F equals MA. So since we have 2 of the 3 in the equation that only have 3 variables, we'll go ahead and we'll plug in our values. Now, once again, make sure that the force that you're plugging in is this 193, not this 200, because this 200 is not going to go into acceleration. Only the 193 we solved for earlier will. And we have that 193.19 over 45, and we get acceleration of 4.29 meters per second. So we'll go ahead and we have this acceleration now. Now we want to find an equation that has all these variables, VIT, VF, and A. We look at these equations right here and we pick the only equation that has those 4 variables, once again, including our unknown, which we now know the acceleration. We plug in our values starting from rest, accelerating at the 4.29 that we solved for 2 seconds here. And so we get a final velocity of 8.58 meters per second. So in this case, we actually do know that it started from rest. So we do know the final velocity is going to be 8.58 meters per second.